Okay, let's take a look at lesson 3.8, implicit differentiation. Now, after you get used to the techniques, I want to make sure you understand why we have these techniques. And again, you've maybe read through this already or seen enough videos to get a sense of how we have this process compared to our original process. And it starts with when we were first taking derivatives, we took derivatives with explicit equations, where it was y equals. So you can see we have y equals. And so that made it a direct method. We can find the derivative in direct methods, right? Versus implicit, where we have equations such as x squared plus y squared equals 25, where it's not y equals. So to find its derivative, we could do two things. We could rewrite this equation in terms of y equals, and you can see when you do that, you end up with y equals square root of 25 minus x squared, and y equals negative square root of 25 minus x squared, which gives you this circle. So this technically, you might recall, is a circle with a radius of 5. Now this is not a function, but it still has rate of change. As my x value is increasing, what is happening to the y values at certain points? And so we're still interested, right, that we have these complex looking graphs, as it says on the right, complicated or complex functions or looking graphs, that we still care about the rate of change. We just have to come up with a different process to find the derivative, to find the slope at a point, right, on that curve, the slope of the tangent line of the curve, right? Y equals. And so that's what we mean by that term. So there's a strategy, our book, there's a strategy here that our textbook uses to describe, and I'll go over that again, just in case I think my internet went out a little bit, that we have this technique of implicit differentiation, which allows us to find the derivative of implicitly defined function without ever having to solve for the function explicitly. So you don't have to solve for y equals. We can still find the derivative of the function. So problem solving strategy here is kind of the direct method to do that. Take the derivative of both sides. Now, the key is that when you have x and y, and again, this gets more complicated later with 3 variables, z's, but whatever your 2 variables, we're calculating the derivative with respect to x, right? That's what we're starting with. We're assuming x is the function we're taking the derivative with respect to, hence the d sine x dx, right? And so when we're going to find it, it's always with respect to x. And if there's another function, another equation, we're assuming that that variable is with respect or is a function. Like it says, y is a function of x. So when we take the derivative of that, it becomes like a chain rule. We still have to take the derivative of the inside of that function, and hence you have the dy dx. Once you have that, you isolate dy dx, and you're solving for the derivative of y with respect to x. So in this problem here, let me give you an example. What I mean here is, you look, right? We look here and you're taking the derivative here, right? The derivative of x squared, derivative of y squared. So this really becomes a chain rule. You're going to take the derivative of y squared with respect to x. So it's 2y, which is your classic power rule. But then technically we're saying y is some function that we don't know, right? Because it's mixed up in here. It's so when we do the 2y times the derivative of the inside. So this becomes right here, we're basically using a chain rule. If I can get that in there. Yeah. So that's where that dy dx, and this is a constant. So the derivative of 25, its rate of change is 0. So that becomes a common thing we do. And sometimes you get confused. What do you mean? It's the derivative of a constant, which is 0. Now, this is something, I don't want to confuse you, but something I share with many students after they have an idea. We are doing the chain rule here technically because this becomes 2x. And if x is a function of x, technically, right, it's dx dx, just like we're here, dy dx. But this is just equal to 1. And so that's why we never write it, right? Because that equals 1. So we just become standard that we don't include it, but technically we can think of it as a chain rule also, the derivative of x with respect to x, it equals 1. And so it's consistent. We just don't write it. But that's why when we do the y, we have the dy dx as you get through all those problems here. I want to make sure you highlight so you can see there is consistency. It's just that we don't write it because it's dx dx, which equals 1. Okay, the derivative of x is 1 when we do that. The function inside of x is x. So that's why when you see it, you don't see in these things, you go through it, you don't see the, as you look at this one here, x cubed, you take the derivative of 4x, the derivative of 4x is 4, right? Again, times the derivative of the inside, which is again 1. So we don't write that dx dx. That's why, again, we do write the dy dx because y is a function of x, which we still don't know. We're just saying it is the derivative of y with respect to x. It involves factoring many times to do that. You can find second derivatives as you go through that. The same things apply, right? You have a circle. We want to know the tangent line. Again, it's important to realize why we want to know the tangent line, right? Look at this example here. Look how complex this curve is. It's a awesome looking curve for y cubed plus x cubed minus 3xy equals 0. It's pretty complex when you look at it here. And then we just care about, in this case, we want the equation of the tangent line at the point 3/2, which is right there. Now, it's so interesting in that, why do we care about these tangent lines? These tangent lines are approximations for this complex looking function. So what I mean is, and this is such a big idea, an important idea, that when you find the equation of this tangent line, right, right here, if you look carefully, right in that spot, the line and the curve are identical pretty much. The line, right, the tangent line approximates, let me spell that again, approximates the curve, right? But right there, this orange line is identical. It's on top of the blue line. It's almost the same curve. And so why we care about those tangent lines is that we would rather use, I can then substitute and use the tangent line in place of this complex formula. So I can find values, right? I can find values of this. So when you get y equals negative x plus 3, that equation is pretty much then representing this equation. It's like it can substitute for it in that neighborhood, in that space. Y equals negative x plus 3 can substitute, be in place of that. So now I know the rate of change of this function. It's really just -1 right here, the slope of it. We can also use it for calculations. If I want to find the value of this function, I don't need to use this complex curve. I could use this as an approximation. We're very good at approximation. So that's what we're doing with implicit differentiation. We're going to end up using this in the next section for related rates, which becomes, I think, probably one of the most challenging sections because of the word problems. There's an infinite amount of problems we can do. From the homework, there's a question I want to highlight. Again, remember, this is my homework help that I try to give you some guidance on as you look at them, and then you have the embedded help videos. But there's one here where I solve where, again, see, it's y equals already, so you don't need implicit differentiation, but technically you could, right? I can cross multiply and then take the derivative of both sides, and then you end up with, you don't have to use the quotient rule. It emerges through implicit differentiation as you do it, or just leave it y equals, and when you do it, you get dy dx on the left, and then just take the derivative normally on the right. So you technically are using implicit differentiation. The only reason you don't call it that is because it's not y equals. But when you write it in this form, now you have it in implicit form, and then you can take it without the quotient rule. I don't know if it makes it easier, but it's just something to be mindful of.